with n equal 4, find the exact answer by integration. Is it over underestimate and the error bound? And find how many trapezoids required to get error less than 10. Third, right small. That's a lot. Anybody else not take the test and need to take the test? Okay. We'll go over the test tomorrow. Is it 2424 or is it 222 on the inside? 222. When do you do that 2424 stuff? Simpson's rule, yeah. Cassidy's rule. Wouldn't it be crazy if you're related to Simpson, Cassidy? Come on, have fun. Say, yeah, maybe so. Feeling 113 over 16 for my estimate. How about you? you get for an error bound?
2.
Agree. Seven-ish, maybe? Remember, you must express n as an integer, so you need at least how many integers? How many trapezoids? 170. Okay, always round up, no matter how close it is to the lower bound, you always round up. You follow? Okay. That works. Cool. Okay. This, I feel like I could be a billionaire right now if I would just pay attention in calculus a little better than algebra. Okay, because back in the day, I was thinking if you wanted to make a perfect copy of something in 3 dimensions, couldn't you just take a magical box? Say I wanted to make a copy of this orange rock, right? Now, couldn't I take sensors and measure the distance to the edges from lots of different angles at the base level? Yeah? And therefore make a copy of the cross-section of the lowest level. And then if I just took my sensors and moved them up a little, then I could measure the distances from all different angles and get a new cross-section. And then reproduce that cross-section off to the side. And then measure a little distance and a little more, and just keep getting cross-sections and copying those cross-sections, and boom, you've got a 3-dimensional copy. And boom, I just invented the 3D printer, but I didn't. So I wish I would have. If I would have thought about that, I would have made $1 billion, gazillion dollars. But that is the idea of today's lesson. Copied cross-sections, or volume by known cross-sections. Now, this, if you're an arty person, you're going to love today, because the pictures are so cool. They are really cool. If you're not an arty person, you'll get better with time. You'll over the course of the lesson, many people said, oh, that's better. Actually, I can tell what that says. All right, so check this out. If you would, consider ye old 2-dimensional graph of the square root function. And we're going to, just like if I were to take this, if you looked straight on this paper, then it would appear to be rectangle, yeah? But if you look at it with perspective, then it starts to look like a parallelogram. Actually, it looks slanted, yeah? If you look at anything from perspective, it starts to look more like this. Okay? Oh, you haven't seen nothing yet. All right. Now, you're looking at it at an 8, yeah? Or like you're graphing it. Never, I won't even say it. All right. You follow? Now, topic of the day is going to go a little something like this. Imagine if I built off of that land with stacks of three-dimensional figures. Now let's say maybe that I wanted to put little slices or stacks running that way. Now I could do lots of geometric figures here. We'll typically do geometric figures. This is going to be so cool. So this, imagine if off of each of those slices I put a little square. Now if I put a little square, then that would be like that. And this, then when I go this is a little longer, so now the height is going to be a little longer. And now the height is a little longer and a little longer. And so as we get further and further from the origin, the base gets bigger, so the height gets bigger, and you get this three-dimensional kind of figure. Now, that's great, but it doesn't have to be squares. I understand you can't do this, but I will. Say instead of squares, it was triangles. Then you'd get this ridge like that. Or maybe semicircles. Like that. And all that's great, but it doesn't even have to be going that way. It could be going this way. In which case, look more like that. So I like cornucopia for Thanksgiving. You know, like there's some bananas and there's some grapes. You know, do you guys still draw corn? Do they still do that in Thanksgiving in kids' school? Never mind. All right. Now, your objective, should you choose to accept it, and you do, is to find the volume of those. Now let's start with the square case. Same region. And the cross sections, or the segments in the plane of the base, they're running parallel to the y-axis or perpendicular to the x-axis, if you like. And the cross sections that we're going to use are squares. So a little bigger each time. I want the volume. Find the volume. You and your math amigos should be able to do it. The other class was able to do it. Go. You can draw as many as you want. There are infinitely many. So this has to be curved. This has to be square root function, just like the base does, because they're square. I will also say this: if you use your calculator, you are ridiculous.
So the base is always going to be Okay, let's just try one square.
The base is going to be
No.
that is the line.
Okay, okay.
The volume of browser and the x-axis.
The height.
Yeah. So, but is it really just a really nice Yes. It's always an engine. Oh,
Did we
I know.
do it?
No, that's
What do you have?
We got ITX, we got
from
0 to
Function is the limit, and then the square is the function. Because it's a square.
Yes.
Because that's
Yeah.
something else to this, so that's what she mentioned.
I
I'm just throwing an X.
How we doing? Like I said, if you know what you're doing, you should get pretty much the easiest intro of all time.
Well,
Yeah, you should just be integrating it.
Yes,
Oh, let's go.
we didn't do that.
Dude, Jordan, how does it feel to we got it? And you said,
honestly, Eric,
Feels as if we're fun all day.
okay, answer is
X.
8.
What the?
Okay, it's the sum of many of those slices. And the area of the base is the area of a square. So what's the square? So it's this base times itself, yeah? And what is the base of each slice? It's just the function, right? Do you agree? So the volume is the sum of many side squares from 0 to 4. It's 1/2 x squared from 0 to 4, or 8. It is 8. Okay? Notice there's no pi in there. Why not? Yeah, you're not. There's no circle component to this. It's not like we're taking this and revolving it like a revolution. There's no circle component. It's just straight up geometric areas. No circle. All right. Now, let's say that we took this same region from 0 to 4 under the x squared, but this time the cross section's parallel to the x-axis. So our slices go this way. Now they're still squares, so they're going to be really little in the background and gradually get bigger and bigger and bigger as you approach the foreground. It looks like it's going to swallow yes, right? Find the volume. Okay, this one you may use a calculator. What is numerical?
I'm an advocate for send.
So the base is square
Yes.
The height is just square. I think that's well, that's why. That's why I'm just like, no, there's why. Why? I think why square.
So why did we again, how do you choose this? Each will be a different AB, guys. Area and base but the height is always dy.
How would you take that?
Yep. I got something 17-ish. We're like 356.15. Okay, so by far the biggest error is identifying this distance. Now, say, wouldn't you agree that there's some segment like this when the curve is at 1? How long is that side? Is it like the x, is it 1? Or is it more like 4 minus 1? So this is 3 here, then 2 here. So this distance here is not x, it's 4 minus x. Now that's great, but the curve is being integrated with respect to y. And so where I would normally want to say, okay, so I'll crank out 4 minus x quantity squared dy, I would have to then say, well, what is x in y's equivalence? And x is equivalent to y squared. So it would be the integral of 4 minus y squared, quantity squared. Notice it's not squared each like a washer. It's the whole quantity squared. And the limits from 0 to 4? 0 to 2. Okay? All right, and that is 17-ish. All right, now let's try. That's squares. And squares is the most common, but sometimes you'll see rectangles. So imagine if you had a different region. So let's sketch the region in 2 dimensions, then go to perspective. Here's F, obviously, and here's G. And the y-axis, so we're talking this region here. Right? Now, if we graph that with perspective, it would be more like that region. Right? Now let's straighten or see where the cross sections go parallel or perpendicular to. It says the cross sections are parallel to the y-axis, so parallel to the y-axis. Obviously, we can make that. I think that's obvious. Okay? And then last but not least, the shape. Now the shape here, they're rectangular cross sections with height half the base. So at this point, at the y-axis, the base is 4. So the height would be 2. And as those segments get smaller and smaller, the height will be half of smaller and smaller. So what will happen as we go to that rightmost point? So they should get smaller and smaller and smaller. So it should go to a point. Because if the base goes to 0, then the height goes to 0, right? Might help then to draw a representative cross section. That's really the phrase of the day, cross section. The thickness is the height, and that is dx or dy here. dx. This Now, this is one of my, over the course, I taught this really badly my first 2 years. And I was like students, and I was in a rush to get the equations. It's so much more clear if you go slowly with the geometry and then go to the equation. So wouldn't you agree that the area of the base is a rectangle base times height, yeah? And they tell you in this case that the height is half the base. So if you put that in, then the area of the base could be thought of as just 1/2 of the square. Now that's easy to put into the equation or into the integral. Volume is 1/2 can go out front, square of a base segment. Now, the base segment, that's an upper minus lower case, right? So how would you find that base length? You may use their names, you don't have to use the equation. G minus F or F minus G? G minus F. G of X minus F of X, quantity squared. Now on the AP test and in my class, if they use function notation, use the names, G and F. If it's Y's, well then you've got to write the equations. You can't call them Y, obviously. So the limits of integration, maybe we could find the intersections just yes and check. What are they going to be at? Remember, we're looking for the x of the intersection on the right-hand side. Yeah, 2. Okay, so from 0 on the left to 2 on the right, boom, we got our bone. Are we good? Okay, try the next one. Try the next one. How's it going? I think you're still working. Probably tells me you're doing it the hard way. All right. Okay, I feel like an integral from 0 to 2 of x squared dy, which I'd have to put in y terms, so y squared dy, if y equals x, works for the bottom half. But the top half, I would have to change over once you get to the upper half from 2 to 4. The slices start to have more like a distance to g kind of feel. So that's more like 4 minus what? We?
Yes.
4 minus what? Do what? That works. Does anybody have an easier way?
But you also had the 2.
What?
For 2 for the height.
Oh yeah, that's the, oh yeah, there's no square here, sorry. What's the area? The area of the base should just be x times 2. And so there shouldn't be a square there, my bad. It's more like 2 times that and 2 times that. Right? Okay, now, what's easier? In this case. Maybe that. What's the area of the base? Now, think of it now instead of like a calculus shape, but just a geometry shape. Isn't the area of the base just the congruent figures in parallel planes? So something like the triangle. Okay. The base, here's the best place to go for the base and the height. What's the base of that triangle? 4. And what's the height of that triangle? 2. And what's the height of the prism? 2. And so, now, that obviously doesn't work every time because that's not a prism. This is something totally different. So, but if the height is constant, geometry is probably the best way to go. If height equals a constant, think to use geometry. Cool? Okay, let's go a little more challenging here. Say you have the same region with the 2 lines making a triangle with the y-axis, and this time the slices are back to being parallel to the y-axis, like that, but now they are equilateral triangles. I could do better. Okay, so equilateral triangles are like that, yeah? Okay. So, the thickness, is it dx dy? Dx. For the area of the base, okay, there are actually 3 ways to find area of the triangle in mathematics. What are they? Base times height divided by 2. What else? You used to do that after you learned trigonometry. Yeah, something with a sign. 1/2 AB sine C. Then there's the little known Heron's formula. Do any of you know Heron's formula?
Oh, we did that. I don't remember what it is, though.
Okay, if you have any old triangle with all 3 sides given, then Heron's formula uses the semi-perimeter, which A minus, or S minus A times S minus B times S minus C. That's not useful in this case. All right, now this, you use this when you have isosceles triangles. This, I beg you, please use for equilateral triangle cases, like we have here. It's so much easier, and you'll see why. For equilateral triangles, well, first thing is A and B represent the sides of the triangle. If it's equilateral, then A equals B. Okay? Likewise, if it's an equilateral triangle, angle C is the angles of an equilateral triangle are 60 degrees. They must all be 60 degrees. So the sine of C will be sine of 60 degrees, or root 3 over 2. So for equilateral triangles, we can conclude that the area 1/2 AB sine C will be nothing but 1/2 A squared times root 3 over 2, or root 3 over 4 times the side squared. And that gets pretty doggone clean. So for this problem, the volume is root 3 over 4 for all the equilateral triangle components, the 1/2 and the root 3 over 2. And we just need to find what is a side and square. What is a side of the triangle? How would you find those edges? G minus 1. And it would be back to x limits of integration, so 0 to 2. Okay? That's the easiest way to go for equilateral triangles. Some of these require some serious reading and even rereading. Try the next one on your own. This one will draw on some geometry skills, I hope you still have. Test out those geometry skills. Thank God I teach this school. Yes, sir. Use this one. Shoot. Sorry, I see what you're saying. This I was totally locked into using the previous graphs, wasn't I? Sorry. Not sure why it took you so long to say something, but thank you, Eric, only. But for this one, let's do the graph that I'm giving you. It looks like this in 2 dimensions. And I believe they meet at -2 and 1. Make that graph look nice. Isosceles right triangles with a hypotenuse in the plane of the base. That's just remember what I said about being really careful with your geometry first, and then your calculus is really smooth out. Try to do as much geometry as find that the area of the base is actually a very clean. This one I suggest you use base height divided by 2, not 1/2 AB sine C. Okay. What's the height's relationship to the base? So do you agree that if it's isosceles right, these base angles have to be 45 degrees? Okay, if that's 45, then this has to be 45. So this is like a baby isosceles triangle. And this side here must equal that there. So what is the height's relationship to the base? It is half the base. Therefore, the area of the base, instead of base height divided by 2, is base half base divided by 2, or base squared divided by 4. That's pretty good. Okay, now you do your calculus. That's hard enough, that geometry, but clouding it with all the calculus equations, and all that's too much. Okay, break it into geometry first, clean as you can get, one variable only, and then go to your calculus. So if the area of the base is base squared over 4, and the height or thickness is dx, then 1/4 out front, and what is the base? G minus f or f minus g? G minus f. Quantity, all quantities squared. Again, you can see how, when it will all be thrown at you at once, and how you can easily say get where the squares are on a Washer problem versus the squares on a problem like this. You know, on a Washer problem, it's square minus square, but here it's square of the difference. So you have to be conceptually careful. Do not try and memorize jack nothing. It's all conceptual. You with me? Okay, last but not least, let's go semicircles. These are my favorite. Okay, so imagine the sine curve up until it maxed out at pi over 2. Okay, this is actually, students actually find this the second easiest one to find squares. All right, now, in this case, they say parallel to the y-axis, so jump to the stripes are parallel to the y-axis, and semicircles, so starting at nothing and then getting bigger, 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 and bigger. Kind of missed, but you get the idea. And we want the volume of that, yeah? There is definitely a shortcut, and as I've said over and over again, geometry first. Clean geometry first. So let's do clean geometry first. The thickness, yes, it looks like a taco. The taco problems, as they will be soon called, I'm sure. What's the thickness, dx or dy? Dx, all right. The area of the base, geometrically speaking, how will you find it? Pi r squared divided by 2. Now here's the thing, though. We don't really, I don't want to get into what's the halfway point or what's the halfway point. We don't know the radius here. We know what? The diameter. So transfer over to diameter. Instead of radius squared, we'll talk about the diameter half. Isn't the radius the same as half the diameter? Therefore, in its cleanest possible form, we can find this value by doing pi over 8 of the diameter squared. That is easy. Pi over 8 diameter squared dx. And what is the diameter? Upper minus lower, but in this case, the lower is just the axis, so it's just the sign. Yeah. You can see then how you could use that identity, sine squared identity, if you wanted to do this by hand. Like that. Okay, last one. Try same region, same shape, but this time parallel to the x. You can go home and tell your mom today you learned how to find the value of infinite taco. There is a place to be careful here for sure, and that is the diameter. Is it sine of x? No, that's crazy talk. It has to be a y term. So is it arcsine of y? No. For example, when it's on the axis, is it pi over 2? Well, yes. But here, what is it? It's not arcsine of y, it's pi over 2 minus arcsine of y. It's the total take away the curve. It's actually pi over 2 minus arcsine of y from 0 to 1. Okay, that's it. Nothing to do. Have a nice day. Infinitely many tacos. Now I'm really hungry for tacos.